Hi everyone. So here we are with chapter 11 part 2, and we are still on thermochemistry, and we're just going to talk more about thermochem stuff. Okay, so here's a diagram. This is called the warming and cooling curve, and you're going to get one of these handouts in class if you don't have it already. And this one is for water. Okay, so this is for water. All substances will have their own warming and cooling curve, and sometimes I refer to this diagram as also a phase diagram. So what this is telling us, it's telling us here at this point, okay, this is 0 degrees Celsius. That's the melting point, and that's when it transitions from solid to liquid. And then the boiling point over here will be 100 degrees Celsius. So at that point, that's where it will transform from liquid to gas. Okay, so you can see what's happening here. We have energy that is along the x-axis and temperature is along the y. All right, so notice at this point here, at 0 degrees Celsius, it's transitioning from ice, okay, into water. And notice that the temperature does not increase, so it remains constant. So you're just adding energy to that point. Once it has completely transformed to water, then the temperature, we can heat it up, add more energy, and temperature can increase. And then now we hit 100 degrees Celsius, and then the liquid can transform into gas. Notice as it's transitioning from liquid to gas, the temperature does not increase until that transformation has been complete. And then it can go up to steam. Okay, so if we're going up the stairs, so this is what I call the stair-stepping diagram. So if we go up the stairs, so let's draw an up arrow. So if we're going up the stairs, this is an endothermic process. Okay, and this is just a physical change. So this is going from a solid to a liquid to a gas. It is endothermic going up the stairs. And then if we're going down the stairs, that means we're going in the opposite direction, going gas, liquid to solid. That is an exothermic process, okay? So I want to go back to this diagram, and this first flat part here, this is called the heat of fusion. Okay, so it's called the heat of fusion, and this value is 334 joules per gram. So that's how much energy it takes per gram of substance to transform it from ice into water. These numbers here, like heat of fusion and this other one that I'm going to talk about, you don't have to have these numbers memorized. They will be provided for you on the test. All right, then this second flat part over here is called the heat of vaporization. And this requires 2,260 joules per gram. Okay, so it takes a lot more energy to convert the liquid into gas. So once again, you just need to know like heat of vaporization and where it's located, and heat of fusion where it's located. But the numbers I will have provided for you on the test. So if we are going up the stairs, once again, remember, it's endothermic. So if it's endothermic, remember the delta H values are going to be positive. So then therefore your heat of fusion will be positive 334 joules if you're going in the endothermic direction. And then the heat of vaporization will be a positive 2,260 joules per gram. But if we're going in the opposite direction, so what if we're going down in the exothermic direction, and we're going from, let's say, gas to liquid instead? It's not called heat of vaporization. It's actually called heat of condensation. Okay, so it's called heat of condensation, and instead of positive 2,260, it's going to be negative 2,260 joules per gram, because it's going in the exothermic direction. So remember, exothermic releases heat, so therefore it will have a negative sign to indicate that the heat's being lost. And then if we're over here, going in the reverse, liquid to solid, that is called heat of solidification. and it will just be negative 334 joules per gram. So notice that the numerical values are still the same. We just changed the sign, whether it's going in the positive or endothermic direction, meaning heat is being absorbed, or if it's going down in the exothermic direction where heat is being lost. We just changed the sign, whether it's positive or negative. So this is where we're going to start. You already have this in your in-class notes from part 1. It's a continuation from those notes there. So turn to that page and find this section. So the first thing we're going to talk about is heat of fusion. So heat of fusion is solid to liquid. Notice that 2 different values are provided for you, okay? This one is in kilojoules per mole, and this one is in joules per gram, okay? I typically just use the joules per gram conversion. Instead, you can always convert your joules to kilojoules, and you can always convert the grams to moles. So you don't really need to have these numbers memorized. And once again, I will have these numbers on the test for you. And then going in the opposite direction, remember the exothermic direction, we call this heat of solidification. So you go liquid to solid. Notice the numbers are the same. The only difference is they are negative because they're going in the exothermic direction. Okay, so here we have this question here. How many grams of ice at 0 degrees Celsius? And then it gives us the pressure. So it's just telling us that it's standard pressure, but we're not actually going to use the pressure value in our calculations. And then we have 2.25 kilojoules of heat. Okay, so the temperature is given to us so that we can find where we are on the diagram, okay? And let's check out this transformation. So we have to figure it out. 0 degrees Celsius, is it asking for a transformation between solid to liquid or liquid to solid? Okay, well, it says how many grams of ice could be melted by the addition of this much energy. So therefore, we are going from solid to liquid. We want to know how much ice could be melted, so solid to liquid. So that means we're going to be using the 334 joules per gram conversion factor, okay? So basically, we're just going to set this up to get our units to cancel. So we have this value here, this number that's given to us, 2.25 kilojoules, okay? And notice here that this conversion factor that I have is in joules, all right? So then let's convert the kilojoules into joules first. Okay, so that means in 1 kilojoule, there are 1,000 joules, okay? Or in other words, you can just move your decimal. You could just move this decimal here 3 places to the right, okay, which is the same thing as multiplying by 1,000, okay? So then once we convert that, then we know that's 2,200 and, 50. So 50. Right, if you multiply that by 1,000, move this 3 places, 1, 2, and then the other one will be a 0. And then that will be in joules, all right? So we start off with joules. So then what do we want on the bottom of the next step? So the units cancel. We want the joules. So we'll put the 334 joules on the bottom, and then therefore the gram goes on top. And then we put this into our calculator. So 2250 divide by 334. And we want to round this so it has 3 sig figs. So then I got this to be 6.74 grams. So that it has 3 sig figs. Okay, so 6.74 grams. So now let's continue on to the next problem. So let's scroll this. All right, now we're on to a question involving heat of vaporization. So remember, heat of vaporization is when it goes from liquid to gas. Once again, kilojoules per mole, or this one is in kilojoules per gram, and I know on the diagram I put that one in joules per gram, so you can convert back and forth between joules and kilojoules. And then going in the opposite direction, so then we have heat of condensation, which is gas to liquid, and then once again, notice the numbers. Numerical values are the same, it's just a difference of a negative sign because it's going down in the exothermic direction. All right, so here we have this problem. How much heat in kilojoules is absorbed? So that's telling us this is most likely going in the endothermic direction. We have this many grams of water that's in the liquid state. The temperature is provided, once again, to help us figure out where we are in the diagram. And this is being converted to steam. Okay, it's being converted to steam. So we know we have a liquid to a gas, right? And then we look over here, liquid to gas, and we're going to use this conversion right there. So we're going to use the 2.26 kilojoules per gram conversion. All right, so let's start off with the number that's in the problem. So 24.8 grams. So if we have grams here, what do we want on the bottom of the next step? Grams, right? So then just the gram part there will go on the bottom. Therefore, the 2.26 kilojoules will go on top. So you can see that the grams will cancel out, and then we're just going to multiply. And it also wants us to have our answer in kilojoules, so then that works out perfectly. So then let's put this into our calculator. All right, so 24.8, let's see, 24.8 times 2.26. Okay, and we want to round to 3 sig figs, so then I found this to be 56.0, and then this would be in kilojoules because the grams cancel. Okay, so you can double check that to make sure I entered it in correctly, and I believe I did. Yep. Okay, so that is how we would use the heat of vaporization conversion factor to solve a problem. So let's go on to the next type of problem. So let's scroll here a little bit. Okay, so this one is involving what is called the heat of solution. Okay, the heat of solution. And so here's the definition: heat change caused by dissolution. Dissolution just means dissolved in water. Okay, it's just a fancy word which means dissolved in water. All right, so in this problem, it says how much heat is released when 2.5 moles of sodium hydroxide is dissolved in water. So notice here they give you the value, okay? So they give you the conversion factor. This is our conversion factor. So let's set up our problem so the units cancel. So we're going to start off with that number there. So 2.500 moles. All right, so if we have moles here, then what do we want on the bottom of the next step? Mole, right? So then the mole here will go on the bottom, and then this will go on top. So then negative 445.1 kilojoules on top, and that's per mole. So moles cancel, and we're going to multiply. And notice there's a negative sign here, so our answer will be negative because this is an exothermic process. So 2.5 times 445.1, and then we get 1,112.75 kilojoules. But let's condense this down a little bit. Let's see, so we need 4 sig figs. Okay, so then we'll round this answer to only 4 sig figs, so it'll be 1,113 kilojoules, and once again, keep the negative in there, and that's it. All right, so this is the last section of chapter 11, and we're going to calculate delta H using 2 different methods, and it kind of depends on what information is provided for you in order to determine what method to use. Okay, so this first one we're going to talk about is called Hess's Law. All right, Hess's Law. So basically for Hess's law, it gives you multiple equations to manipulate. So in this case, we're given two equations to manipulate, okay? And when we add them up together, they have to equal this, okay? That's what we're trying to get. And then we want to calculate the delta H for this reaction using these two equations that are provided here for us. Now this reaction only has two equations that we're going to use. Some reactions will have more than two, like some will have 3, 4, even 5 different equations that you can manipulate to get to the final equation. Okay, so here are the guidelines. So it says if you reverse an equation, you reverse the sign on the delta H. Okay, if you multiply the equation by a number, you're going to multiply the delta H value by that same number. All right, so we're going to do this example here, and it's pretty easy. You're just going to take one thing at a time. All right, so we want C diamond on the left-hand side, and we only need one of these. So we look at both equations that are provided, and it's this one right here that has diamond in it, and it is already on the left-hand side, and it already has 1, and that's how many we want. We just want 1. So the second equation there, I'm just going to write it out. We're going to keep it the same. Okay, we're not going to change it. We're going to keep it the same. We don't need to multiply it. We don't need to reverse it or anything else. So I'm just going to keep it the same. So therefore, the delta H value stays the same. So negative 395.4. Okay, kind of ran out of room there. All right, then the next thing that we want in the equation is we want graphite on the right-hand side. So this first equation is the only one that has graphite in it. But I want it on the other side of the arrow. I want to get it on the right side of the arrow. So I'm going to reverse that first equation. I don't need to multiply it because I only need 1, and this one already has 1 listed. All right, so then I'm going to reverse it. That means I'm going to write it in the opposite direction. So now the CO2 is going to be on the left, and then C graphite goes on the right with the oxygen. And so since we reverse that, then I'm going to reverse the sign on the delta H. So it originally was a negative, so then now it becomes positive. So now that's positive 393.5. Okay, so now we're going to add these two equations up together. Whatever we have the same on the left and on the right hand side, we can cross out. If they are on the same side of the arrow, they get added. Okay, so if they're on opposite sides of the arrow, you can cross them out. If they're on the same side, they get added. So you can see that we have a CO2 here, and that can cross out with the CO2 on that side. So those can cross out. Then you also see we have an oxygen here that's on the left side of the arrow, and that can cross out with this oxygen that's on the right hand side of the arrow. Okay, so then we're left with C diamond, which is on the left side of the arrow, going to C graphite, which is on the right hand side of the arrow, and that's what we're looking for. And then with these delta H values, you want to add them. Okay, be careful when you add them because they have negative signs on them and stuff, so make sure you're careful when you do that math. So then we just want to rewrite this to verify that we did it correctly. So C diamond going to C graphite, and then we're going to put the other stuff into our calculator to get the delta H value. Okay, so let's see, we had negative 395.4, and that's negative, plus the 393.5. Okay, so I end up getting negative 1.9, and the units that are there, kilojoules. All right, negative 1.9 kilojoules. So we get a negative delta H value, so therefore this process would be exothermic. Okay, so there's one last type of problem that I have to show you, and that is involving what we call the standard heat deformation. Okay, so this is just another way that we can solve for delta H depending on what information is provided for us. All right, so the standard heat of formation is the amount of energy that it takes to form that substance. Okay, so this is the symbol for the standard heat of formation. And notice here it says that the standard heat of formation for a free element in its standard state is 0. And so that means that if it's an element all by itself, not combined with anything different, so that includes your diatomic molecules, and that means in its standard state at room temperature, is it a solid, liquid, or gas? And if it is in that standard state, then it will be 0. So to calculate the delta H using the standard heat of formation, we're going to use this equation right here. Okay? Basically, it's products minus reactants. All right? Products minus reactants. Okay? The products minus reactants. And to get these values or these standard heats of formation, they are in your textbook. On page 316 is a whole table of them. And you would look up these values. And so you're not expected to memorize these values. They will be provided for you on the test. And if there is a coefficient in the equation, you would multiply the value in the chart by that coefficient. It is also really important that you pay attention to the states of matter when you're looking up these values in the chart, because they are different if it is a solid, liquid, or gas. Okay, the values will be different. So it is important that you look up the correct one. All right, so the first thing that we're going to do in this sample problem, we're going to look on page 316 in the textbook, and we're going to look up these values. Okay, so let's see. This first one here, there's a coefficient 2. So I'm going to multiply that value by 2, and I'm going to look up CO gas in the textbook, and it says it's negative 110.5. Okay, then the next one here is oxygen gas, and oxygen gas is in its standard state, so this is going to equal 0, and it also says that in the chart. Okay, then we go to the next one. I'm going to put a little plus sign between those. All right, then 2 CO2 in the gas state. So I find CO2 gas. Okay, that is negative 393.5. All right, so now that I found all of these values in the chart, now I'm going to put them into this equation. Okay, so it's the products minus the reactant side. Okay, so this side, these are your products. Okay, remember products are on the right-hand side of the arrow. These are the reactants. Okay, so the products minus the reactants. So then if I want to rewrite this in the equation, I can. So 2 times negative 393.5. Okay, those are my products minus the reactants. Okay, so now let's just do the math. Use your calculator. Okay, so 2 times negative 393.5. All right, so this is negative 787. Make sure you keep track of all the negative signs and stuff. Okay, and then 2 times negative 110.5. All right, that equals negative 221. Okay, so we finish out the math here. All right, so then negative 787 minus negative 221. All right, then I end up getting negative 566. And then look in the table of what units they used were kilojoules. Okay, kilojoules. And that's it. You'll notice that in the table, the units for each of the substances are written out as kilojoules per mole, but when we multiply them by the coefficients, because remember those are moles, the moles get crossed out, okay? So then we just leave it in kilojoules. All right, so that is everything for Chapter 11, Part 2. So you need to know how to use the stair-stepping diagram, like heat of fusion, heat of vaporization, to solve problems. You also need to know how to use Hess's Law to solve for delta H, and then also using standard heats of formation, doing products minus reactants. Okay, so that is it. See you later. Bye.